Alright, welcome guys to another physics class. Yeah, I dropped the link on the speed quiz magnetism that I wanted you guys to attempt. I am here to see your results, but nonetheless, we will do an explanation video because there are other important concepts that are being tested in the speed quiz under the topic magnetism. So without further ado, let's just dive straight into the business of the day. Yeah, let me open the link from the group. Let me open the link from the group. Yeah, I think this is the. I think this is the link. Yeah. All right. Sorry because I have to explain. I won't be able to stay within the timer of the examination because I want to explain, the answers to all of the questions. So it might get to a particular point where we have to do the quiz twice because probably we exhausted the time. All right. So let's start the quiz. Yeah. The first question: a freely suspended compass needle on the Earth's surface settles in a plane called. Alright, let me explain this. Yeah, I believe it's not a new news to any of us here that the Earth has a magnetic field, right? Now, something about the Earth's magnetic field is it is not coincidental with the Greenwich meridian. Instead, the Earth's magnetic field lies at an inclined angle from the Greenwich meridian. Remember from our, if you have done longitude and latitude, that this is called the Greenwich meridian. But the magnetic field of the Earth slants or inclines away from the Greenwich meridian and it will rest along this pole. Something else I need to point to you is, in geography or in longitude and latitude, you know that this is the North Pole and this is the South Pole. But for magnetism, this is the magnetic South Pole and this is the magnetic what? North Pole. So the South Pole is up, the North Pole is down for magnetism. But for geography, the North Pole is up, the South Pole is down, right? So like I said, the Earth's magnetic field is slightly inclined away from the Greenwich meridian, and this line across which this Earth's magnetic field is suspended on is called the magnetic meridian. That is why when you pick a compass needle, in case you don't know what the compass needle is that device that looks like this. That device that we use to know direction. You'd always see the compass needle slanting also, not straight, but in the direction of the magnetic meridian. Do you understand? So by default, the pin of a compass needle wants to align itself. Don't forget, the top of the compass needle is north, and the bottom of the compass needle is south. And you remember the law of magnetism: unlike poles attract, and like poles repel. So look at it: the south pole attracts the north pole of the compass of the magnetic needle, and the south pole attracts the north. And that is why a compass needle would always align itself to the magnetic meridian. Are we together? Would always align itself to the magnetic meridian. So the line is called the magnetic meridian. Please do well to watch this video as much as possible, for as long as possible. You can replay it 2, 3, 4, 5, 6, 7 times, and keep watching it till you understand. All right, let's go on. Also, before I even continue, let me just say something else. Now, if you let me try and draw a magnetic equator. Let's say this is the magnetic equator, right? The angle of inclination, see this angle, between the magnetic meridian and the Earth's equator or the magnetic equator or any horizontal plane. I don't know how you want to put it. It's, don't forget, all these lines are parallel to each other, so the angles will be the same. So the angle of inclination between the magnetic meridian and the equator or any horizontal line is called the angle of dip. See, this theta represents something called the angle of dip, or we can also call it magnetic inclination. So look at it. Let's say the angle between the Greenwich meridian and the magnetic meridian is, let's say, 30 degrees. Therefore, the angle of dip is 60 degrees. And how do we know? Because the angle of dip is the angle between the magnetic meridian, or the angle of is the angle between the inclination of the magnetic meridian from magnetic equator or from the Earth equator or from any horizontal plane, because these angles are still corresponding, so they will always be the same. So the angle of inclination between the magnetic meridian and any horizontal plane on the Earth's magnetic field. All together. So don't forget, we've talked about the magnetic meridian. You should know it's the inclined angle at which the Earth's magnetic field, exists upon. Talk about the magnetic meridian. We've talked about the angle of dip. Angle of dip. That's the angle of inclination between the magnetic meridian and any horizontal parts of the Earth's magnetic field. Horizontal is straight line. Yeah. And how do we measure angle of dip? Yeah, basically the angle of dip is measured with something called a dip cycle. This is the instrument that we use to measure the Earth's angle of dip, or we that used to measure magnetic inclination. Are we together? Okay, let's go. Let's go. This is magnetic meridian. I said, which of the statements is not correct regarding magnetic field? A magnetic field is a region where a magnetic force can be detected. That's very correct. Magnetic field are scalar quantities. Nah, that is very wrong. Why? Because we know magnetic fields have both magnitude and what direction. How do we know? We are taught that field lines comes out from the north and heads to the south. There's the direction. So they're not scalar, they are vector quantities. So the right answer is B. And they said a bar magnet is divided into two pieces. Which of the following statements is correct? Yeah, when I pick up a magnet and I divide the magnet into two, let's say this is a magnet. I have the north here and I have the south. And I break it into two. What I'm going to be having is two new magnets. And what will be the poles on this magnet? It's going to be having a north here and a south here. And the north here and the south here. All together. So when you break a magnet into how many pieces, you form new magnets. Two new magnets are created. That's the correct answer. And I said in storing magnets, keepers are used to. What are keepers? Well, keepers are ferromagnetic materials. When we say something is ferromagnetic, go and watch our previous classes on magnetism. I think the first class talked about type of magnetic materials. We talked about ferromagnetic, paramagnetic, and diamagnetic materials. So remember what ferromagnetic materials are. If you don't remember, you can watch the video again. So basically, keepers are like ferromagnetic materials like soft iron and the likes that we use to prevent demagnetization. Majorly self-demagnetization. It means a magnet is demagnetizing itself or losing its magnetic, capacity on its own. So the entire point of keepers is to reduce self-demagnetization. All right. Next question. Which of the materials is produced from the chemical combination of metal oxides and has a very high resistance to electric current? Yeah, I was supposed to say this in our class where we talked about types of magnetic materials. There's something called ferrite materials or antiferromagnetic. Let me just use the word ferrite. Sometimes it's referred to as antiferromagnetic. Ferrite materials are materials that, you know, they don't respond to a magnet at all. They don't. They don't respond to a magnet at all. They don't even allow a magnetic field. They don't respond to a magnetic field at all, at all, at all. Did you understand it? And the reason why they don't respond to a magnetic field is because there's a very high resistance to electric current. How is electric current related? Remember our discussion where we say once current flows through a conductor, a magnetic field is created around the conductor, isn't it? So if this doesn't allow current to flow, then there's no way magnetic field can pass through this material or can be created around this material. Do you understand it? So their resistance or their resistance to the magnetic field, we call them ferrite substance. That's the answer. Yeah. What does Lenz's law of electromagnetic induction state? Yeah, in simple terms, Lenz's law tells us that when you move a conductor, if you move a conductor or a magnetic field relative to one another, it means you could move the conductor towards or away from the magnetic field, or you could move the magnetic field towards or away from the conductor. So if you move a conductor or a magnetic field relative to one another, okay, or in relative motion, an EMF is induced in this conductor that wants to oppose. EMF is induced in such a way that this EMF wants to oppose a change in magnetic flux. It doesn't want the magnetic flux to change. That is what the Lenz's law is telling us. When I have a relative motion of the conductor and the magnetic field, there is going to be an EMF that is going to be induced, which is going to cause a flow of current that would want to resist a change in the magnetic flux. And don't forget, we said the current that will be induced is called the eddy current. They are very, very important details. Yeah. So, which answer is closer to anything we have said? Yeah. The answer is B. The induced current is in such a direction. The induced current is in such a direction to oppose the change producing it. That's the magnetic flux. Yeah. So the answer is B. Now, Lenz's law is essentially a statement of, well, the answer is the law of conservation of energy. Do we remember the law of conservation of energy? Right. The law of conservation of energy made us know that in a closed system, the word here is a closed system. What is a closed system? A system that doesn't interact with the environment. It doesn't lose energy to the environment. The net change in a system before a change occurs is equals to that, or the net change in a system before the change occurs, or the net energy. Don't let me say the net change. The net energy in a system before a change occurs in the system is equal to the net energy after the change has been completed in the system. What does this mean? It means if I have a closed system, if there is a change in this system, so far as the system is closed, it doesn't interact with the environment. The sum of all the energy would be the same before and after the change in the system has occurred. It means when there is a change in the system, because the energy will be the same, what would the change just do? The change will transfer the energy from probably one form to another form, probably from like mechanical energy to like thermal energy, or from like mechanical energy to electric energy, just from one form of energy to another. Now look at Lenz's law. Don't forget, in Lenz's law, two things are required. One, you have to move a coil or a magnetic field. Now, when you move a particular thing, there's mechanical energy in that system. Mechanical energy in the form of potential energy and kinetic energy. You should always know that. So when we have a moving situation, any moving part or any moving object, there's always a mechanical energy, or there were always mechanical energy in the form of potential energy. That's energy stored and available to do work, and kinetic energy, the energy in motion. or the energy of motion, whatever you want to put it. Um, what Lenz's law made us understand is as you are moving this coil towards the magnetic field, or vice versa, the kinetic energy is being converted from kinetic energy into current, which is electric what? Energy. And this electric energy too is still converted back into another energy that wants to oppose the movement of the magnetic flux. So look at it, energy is just being transferred from one form to another form, which keeps the total energy in the system the same. So it's basically an explanation of conservation of energy transfer from one form to another. And that is why if you look at Lenz's law, if there is no movement in, or if there is no relative movement in either the coil or the magnetic field, and there is no induced EMF, which will lead to no induced current. And since there is no induced current, there is no energy in the system basically because there's no mechanical energy in the first place. And because there is no mechanical energy, current can't come from thin air. So there's nothing to convert. So there's no electrical energy at the same time, which still follows law of conservation of energy. Energy don't just come from nothing. They have to be converted from one energy into another energy. Now the next question, a bar magnet is placed near and lined along the axis of a solenoid connected to a galvanometer. The pointer shows no deflection when, and let me try and give you a quick diagram of what that looks like. Imagine this is a solenoid. And this is connected to, let's say, a galvanometer. What does a galvanometer do? A galvanometer, reads and tells us the direction of flow of current. And the something about the galvanometer pin will always deflect in the direction in which the current is flowing. If the pin is deflecting this way, it means current is flowing in this direction. Are we together? If the galvanometer pin is deflecting this way, it means current is flowing in this direction. Are we together? Now we remember that if we have a solenoid and we have a magnet, right? For there to be induced current, there have to be an induced EMF first. And for there to be an induced EMF, there have to be relative motion. It means it has to be moving, it must not be stationary, right? If there's relative motion, there's going to be induced EMF and it's going to be induced current, which would cause the galvanometer to deflect either to the left or to the right. But should both of them be stationary and there is no relative motion, then there is no induced EMF, which means there is no induced current, which means the galvanometer pin would not deflect. So the pointer shows no deflection when the answer is no relative motion between the magnet and the solenoid. All right, the next question, the relationship between the directions of the magnetic field, the current carrying wire, and the motion in a motor or in a motor, any way you want to pronounce it, is remembered using, you have to be careful here. I know what you are thinking, you're thinking about the right hand grip rule, but you have to be careful here. The motion in a motor. What is a motor? A motor is anything that converts electric energy into mechanical energy. What is a generator? A generator is anything that converts mechanical energy into electric energy. A very good example of a motor is a fan. Why? Because fan will convert electric energy into motion. That's mechanical energy, force, motion, basically, right? And give me another example of a motor. I think a blender. A blender uses the principle of motor system. Blender, because it converts electric energy into motion. Basically, that's what the motor is. And what is a generator? A generator is something that converts mechanical energy, motion, into electric energy. For example, a wind turbine. Have you seen a wind turbine? That's solar energy that uses wind. When wind blows that the hands of the fan, electricity is generated. That's a generator, isn't it? Yeah, the generator that you use to power your house is too are generators too, because the movement of the coil generates the electric energy that we have. Yeah. So when we have motors and generators, yeah, there is one law that describes the relationship between the motion in the gener okay, let's start from motor. In the motor, the motion in the motor, the direction of the magnetic field. Now look at it, there are three elements here: field and electric current. For the right hand grip rule, there are only two elements. And what are the two elements? Direction of the magnetic field and flow of current. Only two elements to watch out for. So the right hand grip rule explains the relationship between only two elements: direction of the magnetic field, that's B, and current. But when the element becomes three, whereby there is motion now, usually in motors or generators, the rule that explains the relationship is Fleming's left hand rule. Listen, we use the left hand rule in motors. Now, I've explained the difference between a motor and a generator for you right now, right? And what is this Fleming left hand rule trying to determine? The motion or the direction of force, anyhow you want to put it. And how does the Fleming left hand rule works? It says put your left hand out and make sure your thumb, your index finger, and your middle finger are at 90 degrees away from each other. If you have done that in the right way, your thumb is supposed to be facing up like this. Your index finger is supposed to be facing straight down like this. And your middle finger is supposed to be facing front like this, like facing your face, such that all these angles are 90 to each other. All the angles are 90 to each other. All the angles are 90 to each other, all of them. And using Fleming's left hand rule, please allow me to redraw. Now that I want to explain. Using Fleming's left hand rule, this thumb, your thumb, let me write it, this is the thumb, is going to be indicating the direction of motion. It means the force will be applied in the up direction. So the motor is going to be moving upwards. The motor is going to be moving upward, or the motion of the motor is going to be upward, or the force is going to be applied in the up direction. Your index finger, this is index, would show the magnetic field. Are we together? Are we together? The magnetic field, that's the direction of the magnetic field. And your middle finger will show the direction of what? Current. One very easy way to remember Fleming's rule is the enemy of man, FBI. Your thumb for force, your index finger for magnetic field, and your middle finger for what? Current. So if for you to use Fleming's left hand rule, you have to know the current, and you also have to know the direction of the magnetic field. You have to know the flow of current and the direction of the magnetic field. Then this will be the only unknown for you to use Fleming's left hand rule. Are we together? So you're just trying to find the direction of force. Now, if current is flowing downwards like this, are we together? And the magnetic field is flowing this way, then the force is going to be applied upwards. What if current is flowing upwards? All you just have to do is rotate your hand. Are we together? If you turn your hand upside down to make sure your current is flowing in the opposite direction of where you put it to be, you're going to be having something that looks like this. Okay, let me just rotate it once. Let me even rotate it from here. So you're going to be seeing what I'm saying. So if I choose to rotate, let me try and rotate this so you see what I'm saying. If I try to rotate this upside down to show that current is flowing in the opposite direction, now look at it. Now current is no longer flowing downward, current is flowing upwards. Then where will be the direction of the force applied on the motor? It's just going to be down, still using Fleming's left hand rule. Did you understand? Then the magnetic field will not be going to the right anymore, but now it's going to be going to the what? To the left. Are we good? So don't forget, we only apply Fleming left hand rule in motors where electricity is being converted into motion, mechanical energy, whatever you want to put it, into force. Yeah. And for you to use the Fleming's left hand rule, what you are looking for has to be the force or the motion of the motor, and the known should be the current and the direction of the magnetic field. On the other hand, we have something called Fleming's right hand rule. Fleming's right hand rule is applied for generators. Don't forget, generators are devices that convert what? Mechanical energy, that's movement, motion, into electricity. Are we together? So we are going to be using Fleming's right hand rule. And what Fleming's right hand rule is trying to determine is the induced current. So for Fleming's right hand rule, what are the knowns? The knowns are force. So we know the motion, how the generator is moving, and we know the direction of the magnetic field. And how does the right hand rule look? Exactly the same way. Position your right hand in exactly the same way you position your left hand, all at 90 degrees to each other. Now, using Fleming's right hand rule, don't forget the thumb will still represent the motion of the force, the index finger will still represent the magnetic field, and the middle finger will still represent the current. Still FBI we are going to be applying. But don't forget, yeah, we are not trying to find the motion because we know the motion already. We know the direction of force. And we know the direction of the magnetic field. What we are trying to find is the induced current. I don't know if you're understanding this. So when I'm trying to find the direction of the induced current, that's I, and I have been given the direction of force or the motion, and I know the motion as well as the direction of the magnetic field. Therefore, I know I have to apply Fleming's right hand rule. And don't forget, by default, you are dealing with a generator, a device that converts physical movement or motion or mechanical energy into electric energy. What if you know the current or you know the flow of current, you know the direction of flow of current, you know the direction of the magnetic field, but now you are looking for the motion of the object? Then you have to apply Fleming's left hand rule. And by default, you are working with what? Motors or motors. I mean, it's anyhow you choose to pronounce. If you have an understanding of both the Fleming's left hand rule and the Fleming's right hand rule. Exactly. All right, so let's go back to the quiz. The relationship between the magnetic field direction, the current, and the motion. Don't forget, this is no longer two units or two elements like the right hand grip rule. If it was two elements, just the direction of the magnetic field and the flow of current, then it is the right hand grip rule. But now there are three elements. So the answer could be Fleming's right hand rule or Fleming's left hand rule. But there's something that is very, very important. They told us in a motor or in a motor, which rule applies to motors? Fleming's left hand rule. The answer is C. I hope you understand. All right, they say what determines the polarity at the ends of an electromagnet? So when I have an electromagnet is a magnet that was created with the use of electricity. So please, I don't know, images are better to explain shit. Let's say that's a cylinder. Let's say I have a coil coming like this. This coil can function as an electromagnet. All right. Now look at this. This coil could function as an electromagnet. And the question is, what determines the polarity at the end of this magnet? Polarity means where is north and where is what? South. And don't forget, what will determine the polarity of this magnet is very, very easy. Do you know what it is? It's just the flow of current. You know that before, right? It's just the flow of current. It's how the current will flow that will determine the polarity. Don't forget, you are using your right hand grip rule here. We'll just say your right hand rule. And if you look at your right hand rule, pick a pen, wrap your right hand around a pen, and make sure your thumb is facing the north. For currents to flow from south to from south to north. Don't forget, north is the magnetic field, but I'm just telling you. So for currents to flow from south to north, don't forget. What am I even saying? For the magnetic field to move in the direction of the north, or for the polarity of the magnet to have the north, where it is here, then you should know that if you look at your hand, current is flowing from the front of the coil to the back of the coil. Are we together? From the front of the coil to the back. Don't forget your fingertips or your fingernails is showing you the direction, the arrows. So it's flowing from the front to the back. Are we together? And if you use your right hand rule for the south to be here, let me redraw that in yellow. For the south to be here and the north to be here, do your right hand grip rule facing that direction. You know that current has to flow from behind the coil to the front of the coil. And the same thing too, if you know how current flows, then you can know the direction of the magnetic field. Look at it. If current flows from behind the coil to the front of the coil, you just have to do your right hand in that direction whereby it flows from behind to the front. Therefore, if current flows from behind the coil to the front of the coil, automatically the polarity of the magnet is going to be north here and south here. How do I know? Just hold the pen and make sure it is flowing from behind the coil to the front of the coil. Good. So you see that your thumb is pointing to where I put my north here. What if current was flowing from the front of the coil to the back of the coil? What do you notice? The polarity of the magnet is going to be having its north here and its south here. So definitely what will determine the polarity of the magnet is the direction of flow of current. Before we go back to the quiz, let me even test your knowledge. In this situation where the north is where it is and the south is where it is, how would current flow? Would current flow from A to B or from B to A? How do I attempt that? You try it out. Use your right hand grip rule. Make sure your thumb is facing the north you see on the screen. But when you do that, you would notice that if my thumb is facing this north, current is flowing from the front of the coil to the back of the coil, isn't it? Therefore, current will flow from the front. See, this one is from back to front too. So current will flow from the front of the coil. Let me put it in green. From the front of the coil to the back of the coil. Did you understand it? Not from the back to the front, but now from the front. Why is current will first flow from the front, then to the back? You understand? So current will flow from A to B. Let's go back to our quiz. So what determines the polarity of the end of the magnet? The answer is simple, the direction of the current in the wire. Okay, they said calculate the magnetic force on an electron. Oh, this is testing your knowledge on Lorentz force. Quickly explain what Lorentz force is. Now, if I pick a point charge, a positive point charge or a negative point charge, that's a proton or an electron, depends on how you want to say. I put this point charge in a magnetic field. Let's say this is a magnetic field. If I put this point charge in a magnetic field, this point charge will feel a force that will push it in a direction. And this force that is going to feel is called the Lorentz force. I'll repeat it. If I pick a point charge, let's say I pick a negative point charge and I put it in a magnetic field, this point charge is going to feel a force pushing it in a particular direction. And that force is called the Lorentz force. Yeah. And what can we see about the Lorentz force? The force is going to be feeling, which is the Lorentz force, is going to be equals to Q times V times B sine theta. And what is Q in this situation? Q is the quantity of charge. That's how many coulombs is this point charge. Are we together? How many coulombs? What is V? V will be the velocity of the point charge. What is the speed at which the point charge used in entering to the magnetic field? Velocity of the point charge. And this is going to be measured in meters per second. You know this by default. And what is B? B is the magnetic field density. Or you can call it magnetic flux density, still the same thing. Which is going to be measured in Tesla. And the most important thing now is theta. What is theta? You have to be very careful here. Theta is the angle between the magnetic field and the movement of the point charge. So the velocity of the point charge, however the point charge is moving towards, and and the magnetic field, the angle between them is theta. So let me write it: angle between B and V. Have it together. That's quite easy. What if I put a current carrying conductor in a magnetic field? Yes, he also experiences a force too. So still the Lorentz force, but is now the Lorentz force in that the conductor that or the wire would experience is going to be equals to ILB sine theta. Very easy to cram, it's very easy to remember. When you understand it, it becomes a piece of cake. What is I here? I is the current. The current, the amount of current in the conductor, which is measured in ampere. What is L? L is the length of the conductor or the length of the wire, which is going to be measured in meters. What is B? We know B, the magnetic field density. And theta, we have to be very, very careful here. Now, theta has to be the angle between the current, and the magnetic field. That is theta. So that's the angle between I and B. All right. In this question, we're told to find the magnetic force, which basically means find the Lorentz force. And because this is an electron is a point charge, so we have to use the Lorentz force for point charge, which is this. F is equals to QVB sine theta. And we are given Q to be 1.6 times 10 raised to the power negative 19 coulombs. What else were we given? We are given velocity B to be 3 times 10 to the 7th meter per second. We are given theta to be 60 degrees. And we are given magnetic flux density, that's magnetic field, to be 10 Teslas. Now, just have to plug in all of that into the formula. We're going to be having the force is equals to 1.6 times 10 to the negative 19 times sorry 10 Tesla times velocity 3 times 10 to the power of 7 times sine 60 degrees. Okay, let's do like terms. 1.6 times 10 is 16. 16 times 3 is 48. So we have 48 times 10 raised to power negative 19 times 10 raised to power 7 times sine 60 is root 3 over 2. Basically, we should know this. So I could still do 48 times root 3 over 2 because the calculator you'll be given would not have sine, cosine, and all of that. So you always have to be able to work with your special angles. I taught you that in your math class. So I have 48 times root 3 over 2 we have 41.57. I have 41.57 times. Look at it. This is law of indices. I could just say this is times 10 raised to power minus 19 plus 7. You should know this from law of indices. The same index and this times. So we turn it to plus. So which gives us 41.57 times 10 raised to power negative 12. I can still remove this. I can still put this in standard form. This same thing as saying 4.157 times 10 times 10 raised to power minus 12. I just converted this into this basic standard form, move the decimal point 1 point forward. And this is going to be 4.157 times 10 raised to power 1 plus minus 12, which is equals to 4.157 times 10 raised to power minus 11. Then the answer close to this 4.157, that's 4.16 as the answer is C. Do you understand? If you approximate 157, it's going to be getting 4.16. 7 is greater than 5, add to 5. So 7 becomes 1, add to 5, 4.16. Newtons, please. That's quite easy. So what's the next question? A 10 microcoulomb point charge moves with a velocity of blah 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 blah. We're also told to calculate Lorentz force here. So we are given quantity of charge to be 10 microcoulombs. That's 10 times 10 to the negative 6 coulombs. In case you don't know, 1 microcoulomb is 10 to the negative 6 coulomb. 1 millicoulomb is 10 to the negative 3 coulomb. 1 nanocoulomb, sorry, not 10. 1 nanocoulomb is 10 to the negative 9 coulombs, and 1 picocoulomb is 10 to the negative 12 coulombs. You should remember this from your electricity class. So we are given 10 microcoulombs here. Velocity is 1 times 10 raised to the power 5. The angle is right angle, that's angle is 90. And the magnetic field or the flux density is 5 times 10 raised to the power negative 4 Tesla. Calculate the force. Same formula. Lorentz force is equals to QVB sine theta. Sine 90 is equals to 1, so I could just ignore the sine theta. And I'm going to be having 10 times 10 raised to the power negative 6 times B. 1 times 10 raised to the power 5 times B. 5 times 10 raised to the power minus 4. Let me just put the sine 30, sine 90 so you understand. So I don't confuse so many people. Yeah, let me just join all the 10s together. 10 times 10 raised to the power negative 6 is 1 plus minus 6. That's minus 5. Minus 5 plus 5, that's 0. 0 minus 4 or 0 plus minus 4 is still minus 4. So I have 10 raised to the power minus 4 times all the whole numbers. 1 times 5 is 5. Sine 90 is equals to 1. So it's going to be 5. Final answer is going to be 5 times 10 to the negative 4 newtons. Is there any answer like that? Yes, option B. And they said the force on a charge moving with the velocity v in a magnetic field is half of the maximum. What is the maximum force that a point charge can experience? The maximum force occurs when theta is equals to 90. Why? Because sine of an angle is always a decimal point until it gets to 90 before it becomes a whole number. And don't forget, a whole number is bigger than a decimal point. So the maximum point will be when sine theta is equals to 1. Therefore, the theta will have to be 90. Are we together? So the maximum force, let me write it, F max, maximum Lorentz force a point charge can experience is QVB. Are we together? QVB. Because theta is equals to 90 and sine 90 equals 1. Yeah. When do we experience half of QVB? What sine of what angle would give us half? The sine of what angle would be equals to 1 over 2. If you remember your special angles, you know that the sine of 30 is going to be equals to what? 1 over 2. Are we together? So theta has to be equals to 30 for you to get half. Let's do QVB by sine theta again. F is equals to QVB sine 30, which will give you QVB multiplied by what? Half. Are we together? So the angle has to be 30 for you to have. We've done only 12 questions, and if you look at it, we got all the 12 questions correct. We didn't fail any question. That's where we stop question 12. We are still doing question 13 when the timer ends. See, we didn't fail any of the question. So I'll try and retake the quiz now. I'm going to start from question 13 straight up. I want to retake the quiz. Oh, shit. Let me go back to the WhatsApp and see if I can retake the quiz. But I'm going to continue from the question 13 where we are. Let's see if you can remember the answers on your own. What do you think is the answer of question 1? Pause the video and answer it. If your answer is magnetic meridian, then you're correct. What about question 2? Which of them is correct? Or which of them is not correct? What will be the right answer? Yeah, if your answer is scalar quantity, then you are correct. Pause the video and answer this. If the answer is A, 2 new magnets are created, then you are correct. What about number 4? Pause the video and answer. If your answer is A, you are correct. What about number 5? If your answer is ferrite substance, then you are correct. Lenz's law, easiest law in physics. You should know this. Yeah, Lenz's law tells us the direction of the direction of the induced current, opposing the change in magnetic flux. Good. That's B. Lenz's law is basically another explanation of law of conservation of energy. Try and answer this question. When does a galvanometer deflect? I have explained this before. All right. So what will be the right answer now? Yeah, if your answer is B, you are correct. Don't forget, there are 3 elements here: magnetic field, current, and motion. Don't forget, there's still a new clause, a motor or a motor. So what rule applies to this? Pause the video and answer it. If your answer is Fleming's right hand rule, you are wrong. Or if your answer is Fleming's left hand rule, you are right. Why motors or motors? Try the word motor so you don't confuse it. Left hand rule is the answer. What determines the polarity? Yeah, just apply your right hand grip rule and you should be able to answer this question. The direction of the current in the wire. I think we just calculated this, and let's go and check our solution. 4.16 times 10 raised to the power negative 11. We also just calculated this and see our answer. 5 times 10 to the negative 4. Yeah, so we just answered this question. The force is going to be half, but like I said, when sine theta is equals to half, therefore the angle has to be 30 degrees. Oh, it's like there's a lot of Lorentz Force question in JAM, because all these things are, I think they are JAM. Yeah, they are adapted from my school. Look at it, I brought all my questions from my school. I didn't create any question on my own end. I adapted all my questions from my school. So they are real life JAM questions, which means JAM test Lorentz Force a lot when it comes to magnetism. Okay, this is another Lorentz Force on a point charge. So we know what to do. QBB sine theta, which is going to be, what is our Q? Our Q is, they didn't give you the force on an electron, but you know that the force on an electron is 1.6 times 10 raised to the power negative 19 coulombs. You should know that by default. They give us the magnetic field or the flux density of 0.4 teslas, and they give us an angle. They say it's moving perpendicular to the field. So the angle between the movement and the field is 90 degrees. Perpendicular means 90. And they said speed is 4 times 10 raised to the power 6 meters per second. Let's calculate the force. Therefore, F is going to be equal to 1.6 times 10 raised to the power negative 19 coulombs times 4 times 10 raised to the power, let's just use 0.4. There's no need of standard form. 0.4. Our calculator has decimals. Times V, okay, times V, that's 4 times 10 raised to the power 6. Sine 90 is equals to 1. So I can just say times 1. Easy. So let's multiply all the real numbers there, and let's leave all the power of 10. Let's leave all the exponent alone. So I have 1.6 times 0.4 times 4 times 1. I don't need to times by 1 though. And I have 2.56. Now 10 raised to the power 19 and 10 raised to the power 6 minus 19 plus 6 gives us, what's the answer? 13. So it's 2.56 times 10 raised to the power negative 13 Newton. This is the force. Is there anything close to this? Yes, option B. Yeah, that's it. Alright, this is also testing Lorentz force, but on a conductor, not on a point charge. Are we together? And what is the force for a conductor? Remember, I said F, the Lorentz force on a conductor on a wire is ILB sine theta. I for current, L for length of wire or conductor, B for magnetic field, and theta for angle between B and I. So can we go on? So let's take in the details of the question. The length of the wire is 10 centimeter. If you convert centimeter to meter, how many centimeter makes a meter? Don't forget. 10 centimeter makes a decimeter, and 10 decimeter makes a meter. Therefore, 100 centimeter makes a meter. So to convert this to meter, I'm going to be doing 10 over 100, which is going to be equal to 0.1 meter. Does that make sense? If 100 centimeter makes a meter, therefore 10 centimeter is 10 over 100 meters. That's 0.1 meters. Yeah, the current is 4 ampere and the magnetic field is 0.2 Tesla. Now the question is, what is the maximum force? Don't forget, the maximum force would occur, I told you, when theta is equals to 90, y cos sin 90 is equals to 1. And it is bigger than the sine of any other angles. You understand? So therefore I know that theta has to be equals to 90. So I would say the maximum force, F max, which is going to be ILB sin 90, which is 1. I is current, 4 ampere, times L is 0.1 meter, times B 0.2 Tesla. So what do I have? 4 times 0.1 times 0.2, 0.08 Newton. The answer is A. Please don't do the mistake of calculating in centimeters. Alright, they say a circuit has an area of 0.4 meters squared. What is this question trying to test us? They are giving us area, they're giving us loops. They are giving us. Alright, let's continue. Sorry, I have to quickly do something. Quick transmission. Yeah, sorry, I had to quickly do something. Sorry for the breaking transmission. So let's go back. Continue. Okay, they said the circuit has an area of, okay, they've given us area, they've given us number of loops, and they're giving us a rotation in radian per second. This is testing your knowledge on angular velocity. Don't forget, angular velocity is measured in radian per second. Angular displacement is given as theta. Angular velocity, don't forget, this is angular displacement. Omega is angular velocity, and alpha is angular acceleration. Yeah, in case you don't remember, angular displacement is equals to omega times time. That's angular velocity times time. It's just like displacement is equals to speed times time, velocity times time. Basically the same. It's just angular mechanics. Basic. If you don't remember, you don't have to struggle. Now they are giving us angular velocity. There is a formula that you can use. I'll tell you how to derive the formula, but you don't have to cram the formula. Sorry, you don't have to cram how to derive the formula. You just need to keep the formula in your head. Yes, the formula to get EMF when you are given angular velocity in a coil due to induced voltage is omega NBA. You can say NBA omega. And how did they get this formula? Let's go back to the original EMF formula given by Faraday's law. Don't forget, Faraday's law says EMF is equals to negative N d phi dt. Do you remember this formula? And we know that phi, and we can recall that phi is equals to BA cos theta. Therefore, the phi can be either B is changing or area is changing or cos theta is changing. Now let's imagine cos theta is changing in this situation. Therefore, I could say the phi, okay, let me make it easy for you. I could say the phi is the same thing as saying negative N times B A times change in cos theta over change in time. You don't have to cram this, but this is just how they got this formula, right? And don't forget, we said theta is angular displacement, which is equals to angular velocity omega times time. Angular displacement is measured in radian, angular velocity is measured in radian per second. All right, so I could just say this is similar as saying negative NBA times d cos omega t. This is very, very complex for that mass. If you don't know how to do differentiation, just cramp the formula. But we are almost there. Now, if you differentiate cos omega t with respect to t, first you have to differentiate the trigonometry. You have to differentiate the cos. So I'm going to be having negative MBA times, if I differentiate cosine, I'm going to be having negative sine. So if I differentiate only the cosine, I'm going to be having negative sine of this same function. I have to differentiate the function itself, omega t. If I differentiate omega t with respect to t, it's like you're saying I'm differentiating 2x with respect to x. The x will go and I'll be left with the 2, right? So if I differentiate omega t with respect to t, the t goes and I'm left with what? Omega. If I'm going to be having multiplied by what? Omega. Now I've differentiated this with respect to t. So I'm going to be having EMF to be equals to minus times minus becomes plus omega NBA sine omega t, which can write as sine theta again because omega t is still theta. So I could write it as omega NBA sine theta. Now, the question here says, what is the amplitude of induced voltage? If you remember your classes on wave, amplitude is the distance between the maximum point and the equilibrium point. So if this is a wave of voltage, imagine this is the graph of voltage. It means we need the maximum voltage, the difference between the maximum voltage and equilibrium point. So we have to find maximum voltage. And don't forget, for maximum voltage, theta has to be equals to 90 degrees. Why? Because I'm going to be having equals to 1. Sine 90 is equals to 1. Because for maximum anything, it has to be equals to 1. Therefore, if I'm having maximum voltage, I can say E max is equals to omega MBA sine 90, which is something as saying omega NBA multiplied by 1, which is omega MBA. That's how we got this formula. Do you really need to learn this? I don't think so. I don't think it's rewarding enough to learn all of this shit. So just cram the formula. Whenever you see angular velocity in EMF questions, now you know angular velocity, they give you radian per second. Once you see radian per second, that's angular velocity already. Once you have angular velocity in EMF questions, automatically know that they are trying to test your knowledge of E is equals to omega MBA. So if I use that formula, they've given us omega to be 10 radian per second. They've given us area to be 0.4 meters squared. They've given us number of loops, n, to be 50. And they've given us magnetic field or flux density to be 0.4 Tesla. So the amplitude of induced voltage is same thing as saying E max. E max voltage is going to be equals to omega MBA sine 90, which is going to be omega MBA basically, which is equals to 10 times 50 loops times 0.4 times 0.4. If you press your calculator, what do we have? I have 80 volts. Yeah, that's option D. Okay, the next question, the magnetic line of force. Very, very simple. They're asking what is a field line. Don't forget, the magnetic line of force Come in. Imagine I have a magnetic. Imagine I have a magnet here. Let's say this is North Pole and South Pole. The magnetic line is the direction in which the magnet will move in. Don't forget the direction of the magnetic field will always move out from the north. How do you get that? So that's the magnetic line of force. It's like same thing, the field line. Did you understand it? These are the magnetic lines. That's the field lines. So what is the field line here? It's the path along which a free north pole will move. Basically, don't forget, because the magnetic field always moves from the north pole to the south pole. Do you understand? So the direction of the magnetic field is always from the north pole. So basically, the magnetic line of force is the path along which a free north pole would move. Easy. I said soft iron is preferred over steel for making electromagnet because yeah, the truth is soft iron is more magnetized than steel. It's more preferable than steel, so it is uh, the right answer here. Yeah, like I said, the right answer here is B. It is more magnetized. It get magnetized faster than steel. It has more magnetic permeability than steel. It's easy for magnetic field lines to pass through soft iron and to pass through steel, and it doesn't retain the magnetism that much. It's a ferromagnetic material. It's a better ferromagnetic material than steel. Yes, the answer is it is more readily magnetized and demagnetized as B. Okay, neutral point in a magnetic field. What is a neutral point? It's the point whereby an object can no longer respond to a magnetic field. And when do we have a neutral point? I'll tell you when we have a neutral point. A neutral point is the point whereby an object is out of the reach of a magnetic field. And basically, when you have a neutral point is when the north pole of a magnetic field coincide with the south pole of um, the earth magnetic field. So imagine I have let's say this is a diagram where I have the earth magnetic field. Where's that diagram? Where's that diagram? I want to do this. So let's say this is the north pole of the earth magnetic field. If I have a magnet here and the magnet has the south pole coinciding with the earth north pole, then I'm going to be at the neutral point. Did you understand it? So if the Earth's magnetic field is exactly equal and opposite to the magnet's field, they have a, a neutral point. Why? Because they cancel out. Are we together? So the Earth's magnetic field will cancel out the magnetic field of that particular magnet. I don't know if it makes sense to you. So if I have a magnetic field and one of the poles is coincide, okay, the north pole of that magnetic field is coinciding with the south pole of the Earth's magnetic field, they will cancel out, and that object will no longer respond. Then that object would no longer respond to that magnetic field. So that's a neutral point. Did you understand it? That's option B. And which of the following is the use of split rings? What is a split ring? Now, a split ring is used in a motor, in a DC motor, direct current motor. What is the job of the split ring? Now, the job of the split ring is, don't forget, um, I don't know how I can explain this without diagrams. I don't know how I can explain this without diagrams. But what the split ring does is it reverses the flow of current. It reverses the flow of current in a motor, in a DC motor, a direct current motor. Why? To keep the motion of I need a diagram to explain this. Do I have a diagram? Okay. Let me show you an image of split ring. Share. What am I using? Let me use Google. I want to do that before the exam end. Split ring. This motor image. I need an image. A very, very, oh, Wonderful, 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 wonderful. Oh, I just need only the image. Now they do too much. Let me just go down. Now look at it. Uh, as current flows in one direction, yeah. Uh, See this particular thing here. The armature, we call this in the armature. The hand that spins would only spin 180 degrees clockwise or anti-clockwise. Yeah. So it's going to spin 180 degrees and clockwise and stop, right? So if current is flowing, it's going to allow this armature spin 180 degrees. Now to keep the armature spinning in the same direction to maintain the torque, so we want it to keep spinning like this, to keep spinning like this. The flow of current has to reverse to keep it spinning in the same direction. That's what we use a split ring for. So a split ring job is to reverse the flow of current. So the armature can keep moving in the same direction to maintain the torque. It's very, very hard to understand without an animation. Just keep it in your head that when you have the split ring, the job of the split ring is to reverse the flow of current such that don't forget a full cycle is 360 degrees. So don't forget the armature would only rotate 180 degrees and stop. So every 180 degrees rotation is going to reverse the flow of current again. So it can flip for another 180 degrees. And it's going to reverse the flow of current again. So it can flip for another 180 degrees. And it's going to keep doing that to keep the motion the same, maintain the torque. Do you understand? And keep the angle of rotation in the same direction. So what's the best answer here? To reverse the direction of the coil every half cycle. That's the correct answer. Another answer that can be correct is to keep the torque in the system the same when the armature the same. Another answer is to keep the armature rotating in the same direction. But the best answer in this option is A. Let's submit the quiz. And you can see we didn't fail any question. So please do well to watch this video anytime or for as long as possible till you understand every concept that was discussed here. Yeah, this will be the end of our class for today. Thank you and God bless you. See you in our math class tomorrow. Have a nice day.